Valentine's Day. A day of hearts, of love, and of course, who could forget the beheading of St. Valentine on February 14th, around 270 AD? Oh, you thought this was a video on how to go on dates? No. Today, we're talking about dating things, figuring out how old stuff is. For example, you might already know how to tell how old a tree is, but what about how old a dead body is? Or a really dead body? Or how about how old the Earth is? Or even the age of our universe? In this video, I'll show you how to date these things, as in, tell how old they are. Please don't romance the universe. It's an abstract concept whose vastness is incapable of being comprehended by mortal minds. Dating for beginners. The tree. Tree dating, also known as dendrochronology, is fairly straightforward. Trees grow each year, but the type of tree and its environment affect how much they grow. For trees in climates that have well-defined growing seasons, such as the cold and high latitude regions of the southern and northern hemispheres, this can be directly seen in their trunks as rings. In the growing season, the tree grows quickly with light-colored spring wood. When growing slows, the wood becomes darker-hued summer wood. These look like alternating light bands and dark rings on the tree trunk, where each pair roughly corresponds to a year. Please do not cut trees down. Modern-day dendrochronologists use a borer to take a small cylinder out of the tree and count the rings. For trees in tropical regions, which don't really have these rings, we have to resort to other methods, such as radiometric dating, which we'll get to later. But trees are the easy case. What if the clock has stopped completely? Please do not try this next one at home. How to date a dead body. Wait, that sounds wrong. In general, finding how long a dead body has been dead is a complicated forensic question involving many variables. Two important ones are algor mortis and rigor mortis. Algor mortis refers to how the body cools as the heart stops beating. The body has a high internal temperature of around 37 degrees Celsius. This heat comes from the metabolic processes and blood flow present while the body is alive. When these processes stop, the internal temperature of the body begins to cool down to the ambient temperature of the environment. For average environments and typical body types, this cooling is 0.8 degrees per hour, leading to the Glacier equation. This equation is very approximate, however. In reality, the cooling depends on the ambient temperature, the initial internal temperature, and how much insulating material there is between the environment and the inside of the body. For example, bodies with a lot of fat or muscle cool down slower, and similarly, bodies with higher skin surface area cool down faster. But we can use other indicators, such as rigor mortis. Rigor mortis refers to the stiffening of muscles due to chemical changes after death. As a general guideline, rigor mortis acts in 3 stages. In the first 12 hours, rigor mortis is settling in, stiffening the face first and the legs last. In the next 12 hours, the entire body is in rigor mortis. And in the last 12 hours, the muscles begin to unstiffen. Factors like temperature and muscle mass can slow or speed up this process, so we need to cross-reference with things like algor mortis to be close to accurate. There are other stages of death forensics, such as pallor mortis, or paling of the skin, and liver mortis, the cooling of blood in the lower parts of the body, both of which occur quickly, within the first hour of death. But these all go out the window once all we have left are bones. For fossils, we instead use radiometric dating, the most common being carbon-14 dating. Carbon-14 is a radioactive isotope of carbon. An isotope is an atom with a different number of neutrons, possibly becoming unstable, and the weak radioactive force begins emitting radiation until the isotope decays into a stable state. The rate at which radioactive decay occurs is exponential, given by this equation, where tau is the mean lifetime. For carbon-14, this is around 8,267 years. Most organic organisms contain some amount of carbon-14, as it is naturally produced in the atmosphere due to interactions with cosmic rays and nitrogen. This carbon-14, in the form of radioactive carbon dioxide, makes its way into plants as they conduct photosynthesis, and then to all other animals. To get the age of a sample, such as a fossil, we consider the fraction of carbon-14 to a stable isotope, such as carbon-12, relative to the fraction of carbon-14 to carbon-12 in the same modern-day material. This is because different materials have different fractions of carbon-14 to carbon-12, where plants typically have larger fractions relative to animals. Once we have calibrated for these effects, we can get the modern fraction, and thus approximate the age of a sample as this. However, note that we can only get an accurate result if the fraction is not so small as to be undetectable. So typically, this method does not work past 50,000 years. To get past that with radiometric dating, we need things like uranium dating. Now we're starting to date not fossils, but rocks. Speaking of rocks, how about we date the Earth? This is a bit tricky because rocks on Earth constantly evolve through geological processes, and the old ones are often impossible to get to. However, there are certain rocks that do not suffer from these issues, and some of them must have formed around the same time as Earth did. These are space rocks, or rather, meteorites, space rocks that have crashed onto our Earth. Using the techniques of radiometric dating, we find that the age of the Earth is around 4.5 billion years. This aligns well with radiometric dating from moon rocks, suggesting that the moon formed concurrently or shortly after the Earth. There's actually a special term for using radiometric dating in space, nucleocosmochronology. Since the Earth should have formed around the same time as the solar system, and thus around the same time as the sun was born, we also estimate the sun to be around 4.6 billion years old, which aligns well with stellar evolution models. But this has all been easy so far. We need a challenge. How about we date the universe? It was thought for a long time that the universe was infinite in both space and time, but now we know that's not true. The universe is not static, it is expanding. This means that if we reverse the clock, the universe shrinks down to a point, also known as the Big Bang. We won't go into too much detail on cosmology, the study of the history of the universe, but we will need a bit of math. The evolution of the universe can be modeled in a few parameters, namely the scale parameter A, the density, and a cosmological constant, combined with the Freeman equation. Here, A, the scale parameter, tells us how physical distance expands as time goes on, and the cosmological constant is a constant energy density permeating the universe that causes such expansion. This thing that looks like a P is the Greek letter rho, which stands for density. Specifically, we're interested in the density of matter, although there's also radiation. Matter dominates throughout most of the universe's lifetime, so we'll assume radiation is negligible. We can normalize such that A equal 1 is the current time, and A equals 0 when the universe shrinks down to a point is the same as the beginning of time. Since matter density scales as 1 over A cubed, we can rewrite that Freeman equation as this, where now the right side integral is the same as the age of the universe. Now all we need to do is plug in the parameters and solve the integral on the left. The parameters we have in this equation are not terribly easy to determine, but we can obtain a form that is observationally significant in terms of the Hubble constant and the corresponding density parameters for mass and cosmological constant. Doing so, we find that the universe is around 13.8 billion years old. With physics and math, we are actually able to give a finite number to something so vast. If you'd like to see videos explaining more about cosmology, such as how we arrive at the Freeman equation, leave a comment below. Dating is tricky, and depending on what you're dating, you'll need different techniques. So this Valentine's Day, don't ask someone their age. Tell them the age of the universe. If they stay, they're a keeper.